Let's continue the lecture on the AWS F1. Today, we'll be running the HelloWorld project provided by Xilinx. Once again, I'd like to mention that many of the figures and contents in this part of the lecture are from documents provided by AWS and Xilinx. Today's learning objective is quite simple. We're going to follow the HelloWorld project for EC2 F1 in this link. That is, we're going to build the host application and the Xilinx FPGA binary and understand what this application is doing. Then we're going to learn how to create a bucket, which is Amazon's cloud storage service, and also learn how to create an Amazon FPGA image or AFI. Finally, we're going to run the FPGA accelerated application on AWS FPGA instance. Feel free to follow the link and see more details about this project. In the last lecture, we launched an M5X large instance with the FPGA developer AMI. Let's keep using that instance for running HelloWorld. You can start a stopped instance in your AWS instance menu. The AWS will give you a new IP address. Type that address to your Linux login screen or your PuTTY host address. After logging into your AWS with your key pair, clone this GitHub repository, go to that directory and source vadd_setup.sh script. Then go to the HelloWorld directory and make clean and build the host application and the FPGA binary using the following command: make target equals hardware, device equals AWS platform, all. The last command is going to take a couple hours, so in the meantime, let's try to understand what we're compiling with this command. Go ahead and launch another PuTTY console and log into the same instance. Or if you're using Tmux, you may want a second pane. Go to the source directory of the HelloWorld project and browse the files. There are two source files, host.cpp and vadd.cpp. If you remember from the last lecture, F1 has a host CPU and a device FPGA. For those of you familiar with OpenCL, you'll notice that this is exactly the OpenCL computation model. Host CPU will send the necessary data from the host DRAM to the device FPGA through PCIe. FPGA will store the data in its own device DRAM, launch user-written kernels, and perform computation. And after kernel execution is done, it will send the result back to the host DRAM through PCIe. So the host.cpp, the host source file, is written for the host CPU, and the vadd.cpp, which is the kernel source file, is written for the device FPGA. They actually go through different compilation process. The host source file can be compiled by GCC, and the kernel source file will be compiled by the HLS tool. But VADD handles both compilation processes under the hood. Since VADD uses the OpenCL environment to launch the FPGA, let's see how OpenCL executes its program. We should first compile the program, and then the program will load the kernel that does the computation on the device. Then it will create memory objects like buffers that is going to store the data on the device. Finally, commands like copy data to or from the device or launch the kernel these commands are sent to the command queue. And finally, the context is the environment that holds these OpenCL components. Let's skim through the host code first. You see that it is written in OpenCL. The host code will first look for an FPGA device, and then it'll create a context, command queue, and a program. And then it'll allocate buffers in the device global memory. It is doing it for the buffer in 1 and for buffer in 2 and buffer output as well. Then it'll set the arguments. The 3 of them are memory objects, buffer in 1, buffer in 2, buffer output, and the last one is a scalar variable. Then it'll copy input data into FPGA device memory using the command enqueue migrate mem objects. And then it'll launch the kernel. Finally, it'll copy output data from FPGA device memory to host memory using the command enqueue migrate mem objects and wait until finish. You probably got the high-level idea of what's going on, but if you want to know the details about these APIs, please go to the Kernel site and search the names of these APIs. Now, let's look at the kernel code, which was enqueued in this line of code. The kernel code is the one that is executed on FPGA. It is written in C, but note that Xilinx also provides an HLS version which accepts the kernel written in OpenCL. So if you're familiar with OpenCL, you're welcome to use that flow as well. Now, although the HLS kernel code looks very similar to regular C code, it has numerous progmas. These are called compiler directives, and it tells the HLS compiler how to build the hardware. We're going to learn some of them starting next part, but for now, let's move on. The kernel code is composed of one top function and 4 function calls. Let's look at the definition of these functions in the next slide. This is the function definition. If you look at the code, the first function, load input, is copying data from one of top function's argument to a stream, which is a local memory structure. And this load input function is being called twice to copy another top function argument. And this function is doing some kind of computation on these streams and writing to an output stream. And the last function is copying data from a stream to a top function argument. Right? So now you have seen the kernel code, I'll give you a simple quiz. What kind of computation is this program doing? Well, the answer is actually quite obvious from the kernel name itself, but what's not very obvious is why the program is coded this way. It seems like we can easily combine these functions into the top function, and the whole thing will be easier to read. Well, we'll learn the reason for this coding style in later chapters. For now, let's move on. While we are waiting for the compilation to finish, let's learn how to use AWS Cloud Storage Service. The reason we're learning this is because we're going to transfer the files from the instance we compile the FPGA image to the instance we're going to run the image. I'll explain the transfer process a couple slides later. For now, let's try to create a cloud storage that we can transfer our files to. Now, click on Services and then S3 in the storage menu. Let's create a bucket. This is the cloud storage where we can store our files. Give your bucket some unique name. If it conflicts with other people, AWS will tell you so. Then click on Create Bucket. After creating your bucket, go into that bucket. Then let's create some folders for practice. Click on Create Folder and make one folder named TCP and make another folder named Logs. We're going to use them later for our exercise. You need to set up credentials to use your bucket. To set up your credentials, you need to know your access key. To find this out, click on your IDE on the right top corner. In the pull-down menu, you'll see My Security Credentials. Click that and go to the Access Key tab. And then click on Create New Access Key. Then you'll be able to see your access key. Make sure you download the key files. You will not be able to see the key again if you close this tab. So please click on the download key file and keep it safe and not delete it. Now you know your access key, you can set up your credentials to access your bucket. In your AWS console, type AWS configure. It'll ask for your access key ID and your secret access key you got from my security credentials. Go ahead and type that in. Next, it'll ask for your region name and output format. You can put the region where you have made your bucket, and for the output format, you can put JSON. Then you're ready to use your bucket. For testing, please type AWS S3 ls your bucket name. Then you'll be able to see the two folders we created for practice. Now we are done with the configuration. But if you check back with our FPGA compilation console, you see that it is nowhere near being finished. FPGA bitstream generation typically takes many hours, and you have to get used to waiting and doing something else in the meantime. So you can take a break here and come back after a couple hours. If the compilation process is finished, please search for the XCL bin file. You can do that with this find command. The one you're searching for is under the directory named build directory hardware Xilinx, and there you can find your file named vadd.xclbin. After you obtain the path of the xclbin file, you're ready to transform it to an Amazon FPGA image. The AFI file will have the extension AWS xclbin file. You can type Vidas directory tools create vidas afi.sh, and xclbin equals the path of the xclbin file we just found, and -o equals vadd, and the S3 bucket of your bucket name, and the S3 TCP key equals TCP, and the S3 logs key equals logs. These two folders are the one we created in our bucket. And if you type this command, AWS will start creating your AFI file. AWS typically takes about a half hour to a full hour trying to validate your XCL bin file for any possible problems and convert it into AFI format. If you want to know the status of the conversion, you want to first find for a file named afi_id.txt and look into that file for the ID of your FPGA image. Then type AWS EC2, describe FPGA images and the ID of your image. Then you'll see that the code is pending. Wait until you see the code changes to available. When the conversion process is finished, you can copy your files to your bucket. Use the command AWS S3 cp your AWS XCL bin file to your bucket name, and also copy HelloWorld host file as well. In order to launch the AFI we created, we need to launch an F1 instance. The steps are pretty much the same before. You just need to change the instance type to f1.2x large. But before doing this, you must have asked for an increase of F1 instance limit. Please refer back to the previous part if you have not done this in advance. Also, as I explained in the previous part, not every region has a F1 instance type. So for me, I am using US East 1 North Virginia to run my F1 instance. Let's execute our AFI on F1 instance. As before, please set up the GitHub directory, source the setup file, and go to the HelloWorld directory. We are not going to do the compilation. We are simply going to copy our files from the bucket. Please type this command AWS S3 copy your bucket, the file name to the current directory, and you can do the same on the HelloWorld file as well. Then you want to execute your AFI. Before doing that, please add the executable mode, change mode to your HelloWorld file, and then type HelloWorld vadd AWS XCL bin. After you type the command, what you're going to see is this message that you have succeeded. Now, let me give you some additional exercise for those of you who want to be more familiar with the code. First, modify the host.cpp file so that it will display execution time in seconds. Number two, modify host.cpp and vadd.cpp files so that it will do vector add of double precision floating point numbers rather than the current version with the integer numbers. Before we end, let me give you some general advice to avoid overbilling. As you know, please stop your instance when not being used. Also, please delete your bucket content regularly, especially the DCP and the logs folders. It's very easy to forget that after you create an AFI, there are going to be some files in the DCP and the logs folder. So please delete them regularly. Also, please minimize your F1 usage if possible and use cheaper nodes for development. And please do not overcreate instances. You do not need those SSDs on a stopped instance also incurs cost. So please don't overcreate instances you're not going to use. Also, consider termination of instances if you're not going to use them for a long time. So let me give you a summary of today's lecture. Host.cpp is executed on host CPU, and vadd.cpp is executed on FPGA. And we found that the HelloWorld is a vector add application, and also it takes several hours to create an FPGA bitstream. We used a cheaper instance, M5, to create an FPGA image, and used a bucket to transfer the image to F1, and we executed the FPGA application on F1 instance. And we did these things to reduce the cost of using AWS. So that's it for this lecture. Before we end, please don't forget to stop both of your instances.